So good afternoon, everybody, and welcome to this online technology meeting on industrial laser processes for automotive and electromobility. My name is Antonio Castelo. I'm technology manager at EPIC, in charge of all the laser topics and the laser members as well. And it's a pleasure to welcome you to this very interesting meeting about this hot topic. And also thank you to the support for ILU that they will present a little bit of their activities today. As I mentioned, is a hot topic for several of our members because it's a kind of topic that we understand very important for a lot of laser manufacturers, but we see more and more process monitoring companies appearing and developing solutions for these applications. The use of artificial intelligence, of course, as for example, Marcus will present, is helping to make more efficient tools. Beam shaping, of course, is one topic that we will cover today as well, and also critical in several laser applications, and this is one of them. And we have been, we have been preparing these kind of meetings in the last 1.5 years. We started last year with a battery meeting in Stuttgart, and we saw that it's very interesting for a lot of our members. And that's the reason to continue with some online meetings about this topic as well, to understand what's happening, what is new since the last time we talked about this topic. So we had as far as I remember, laser welding meeting on February this year. So some months ago, and it's good to refresh what's happening there, what is new, new developments, and also new challenges from the industry. And we will continue, of course. So next year, we will have also an in-person event in the north of Italy to talk about industrial laser processes, and automotive and e-mobility is going to be one of the topics. So please take a look to our website, because we will update all the information about the future meetings. And as I mentioned, Northern Italy, September next year, we will have an in-person event to discuss about industrial laser processing in general, and in particular about this topic. And for those of you that are not part of EPIC, this is a short summary about of our members. And this is EPIC, more than 800 companies and research centers, all of them related with photonics technologies. And the goal of the staff of EPIC is to ensure the sustainability of the business of our companies, help them to access to new markets, help them to learn about new potential applications, and also with networking activities to find new collaborators, new partnerships. And this is a short summary of all the benefits that we offer. We organize in-person and online activities to improve the network and the technology knowledge of our members. We also provide access to market reports in different topics, and we help also with the different human resources requests and also investment in case of companies that are interested in being contacted by investors or venture capital companies, or big companies that are interested in buying other small spin-offs or startups with interesting ideas for them. So if any of these benefits you didn't know about it, but you want to explore more, feel free to contact me back to discuss more in detail. And I mentioned the networking at the online and on-site events. I encourage you to go to our website, because we are going to cover a lot of different topics that will be interesting for you. We are reaching the end of the year, so we will be present in a few exhibitions and fairs. So Semicon Europe, where we will have the technology meeting of microelectronics and photonics. Also on Compamed to discuss about laser photonics applications for the medical market, and in the Precision Fair, for example. And we will finish the year with a technology meeting on photonics technologies for medical diagnosis at ICFO in Barcelona, where we discuss about what is new in photonics technologies for medical diagnosis and treatment, and we will discuss with medical doctors about their needs and their challenges for the photonics community. And of course, we will present in San Francisco during the Photonics West. So a lot of activities that most of you know, networking activities. We will have the VIP networking reception on January 28th, several lunches, also the pilot line breakfast. And this year we will organize also an EPIC Summit on optimizing and scaling photonics manufacturing. It's going to be the Monday before Photonics West, Monday, January 27th. So if you are in San Francisco and you're interested in this topic, optimizing and scaling photonics manufacturing, go to our website and you will find the details to participate. And combining with online meetings, not only about technology, that we will talk about very different topics that you can see here, but also to discuss about human resources in our work group meeting, and also with a technology report, in this case, about photonics in AI and AI in photonics by Bruce Bateman. So if you're interested in what's happening with this topic in photonics and a summary about the research of Bruce in different companies, feel free to join our technology report that we will have a presentation online, and then we will distribute the document prepared by Mr. Bateman. And regarding the meeting today, it's very interesting to have wide variety of companies, so integrators and end users, of course, interested in this topic, also components manufacturers that will cover the needs between the equipment and laser manufacturers and the end user and the integrators, and then service providers, of course, software and design, different materials, R&D. So it's very nice to have all this broad range of companies talking about different topics and covering different applications. We will put this slide in the website later on, so feel free to go back and have a look of the companies interested in laser for automotive and e-mobility. And that's everything from my side. So this is the agenda for today. As I mentioned, we will have a very nice set of speakers covering very different topics. So beam shaping, laser blanking application, the role of CO2 lasers that I was discussing with Christian, that we didn't cover this topic in a few meetings before. So it's very interesting to understand what's happening. The challenges and opportunities for the mobility, freeform, beam shaping. So we will talk about all of this in the next couple of hours. And as I mentioned before, it's important for us to have the support of the association. So thank you very much to Dave McClellan, that is the Executive Director of the Association of Industrial Laser Users in UK, ILU. Thank you for being here today. And the floor is yours to present your association and your activities. So Dave, feel free to share your screen.
Okay, thank you very much, Antonio, for the invitation. Bear with me 1 second and I will share my screen. And there we are. Okay, so yes, it's a great privilege for me to be able to come here and present a little bit about ALU for you. ALU is the Association of Industrial Laser Users, and this one slide gives you a kind of a snapshot of who we are and what we do. We have been around for 29 years. We were founded in 1995, so next year we will be celebrating our 30th anniversary. We have currently 178 member organizations and 115 individual members, and they come from 16 countries. So I guess we could be known as UK centered, but we have members around the world. What we do is we put on a lot of things. We run events similar to Epic in some ways. Each year we have a number of workshops, which are one-day events with delegates come along, presenters present, exhibitors exhibit. This year we've had 5 workshops, and that's fairly typical. ILAS comes up every 2 years, and the next ILAS will be in March 2025, the 26th and 27th of March. So mark that date in your diaries. Our events attract over 500 delegates over a 2-year cycle of workshops and ILAS. You can find out more about ILAS from the website link at the bottom of the page, and our other events from alu.org.uk/events. A little bit about our purpose and vision and mission. So our purpose is to grow laser adoption by connecting, empowering, and guiding new and existing users of industrial lasers globally. Our vision is to maximize the benefits of industrial laser technology to society. So this workshop today is a great example of an application area that's key to us as well as to this event. And our mission is to support the acceptance and progression of laser technology through fostering and raising awareness of laser technology and applications, and connecting academic and industrial laser communities. You can see our officers on the right of this slide. Myself as Executive Director, Rick Hallett is currently our president from the SCFC, and we have two vice presidents, Paola De Bono from TWI and Dr. Richard Carter from Heriot Watt. We are organized by a steering committee with 18 elected members, and a very exciting development is our early careers group, which has currently 24 members. So I'd encourage you, if you yourself are in early careers, or if you have anyone in your organization who is in the network of the laser industry in the supply chain and is interested in joining that, to get in touch. So that's my one slide presentation. Thanks very much, Antonio.
Thank you very much, Dave. So again, I encourage you to go to the website and have a look of all the activities that we do. So again, thank you for the support, and yeah, I hope we will continue our collaboration next year, Dave, with ILU.
Yeah.
And yeah, so we can start with the presentations. So we will have, as I mentioned, presentations in different topics. You will have both the chat and the Q&A boxes for discussion, interactive discussion. So please feel free to use it. And please feel free also to use the chat if there is something that you want to share, any challenge, any comment. So let's make it dynamic. And if you want to post any idea, any suggestion, or anything that you want to offer, please feel free to use the chat to interact with the rest of the attendees. And we can go with our first speaker today. It's a pleasure to introduce you, Marcus Kogel-Holacker. He's the head of department and R&D projects at Presitech, and he's going to talk about beam shaping, process monitoring, and AI. So, Marcus, the floor is yours, and thank you for being here from Japan. So, thank you for the time difference also and the effort.
No. Thank you so much. I'm so happy to finish my working day with that impressive meeting again. So EPIC is always a pleasure. Not only online meetings, also in-person meetings. So it's every time I feel really honored to be part of those meetings. And yes, thank you to have the chance to talk a little bit about what happened in the last, let's say, a year. We had a nice meeting in Stuttgart together with EPIC, which was really impressive. Yes, and to be honest, the last times have not been that promising. So there are some numbers. I put on some numbers which were really promising from the year 2020, where everybody thought that e-mobility, the battery, in the battery context, we all as photonics community play a major role. I'm pretty sure we still can, but everything has slowed down. Everything has slowed down. There is not that high speed again, or still, but which does not have any let's say major impact on what photonics can do for the electric production chain, for the battery production chain. If we are talking about e-mobility, I just put on 2 slides because it's some private issue. This is the topic where my youngest son is working on these days. He's with Kion, with Still, or with Linde. So he's working on forklifters, and he's working in the department of batteries. So it's quite impressive what those companies already did in providing power systems which are not based on fossil energies. So you see here they have already deployed possibilities to have energy sources, not only battery style, so it's hybrid, it's lead, it's the classic lithium iron battery, which can be plugged in those forklifters easily because they have the same connectors, the same weight, which is important. Weight is important, which is different to cars more or less, but weight is important in those forklifters. And you see they built 12,000 batteries of that size per year. So it's always a huge market. So it's not necessarily just the cars we are using every day. Nevertheless, the cars we are using every day, they have the applications. They have the applications. I'm pretty sure that I'm not the first one today who says that those applications and the modules and the parts behind are really, really expensive. Which means we must take care of the resulting quality of our laser welding applications, or of, let's say, of the laser material processing applications.
Marcus,
Yes?
sorry for interrupting. Are you already sharing the presentation? Because we don't see the screen.
You don't see the screen? I
No.
think. Okay. 1 second. I said so.
Now it's working, yes.
Okay, sorry for that.
No problem.
So you're fine now? Okay.
Yep. Yep.
Okay. Okay. That was before. So forklifters do have an impact on e-mobility, which is not the car. So whenever you are interested into that, just approach my son, who is working on that topic. Nevertheless, we have cars. We are working on stuff which is really, really expensive nowadays. If you think about the final module, nevertheless, if it's the battery, the packaging, if it's the hairpin and the resulting element. So everything is much more expensive as the final product than it has been in the combustion engine times. But we see the laser as a tool of choice. This is just one of those applications where we are comparing the laser to other joining strategies, resistant welding, mechanical connections, or wire bonding. And you see that in most of the fields, the laser has a very, very impressive advantage against all those others. And as the laser sources are getting cheaper and cheaper, the advantages pay off more and more and more. The same is if we talk about the materials. If we talk about copper, if we definitely talk about steel. So steel and lasers is it's a winning team, definitely. And I'm pretty sure Andreas Heider will talk about that in his presentation. Nevertheless, we need to take care about something which we haven't taken care about, let's say, 10 years ago. And this is the point where we apply the photons. And we have the freedom these days. We have the freedom these days to bring the photons to the right point for the specific application, for the specific material. So it's not necessarily just top hat or Gaussian beam, which has it been, let's say, 10, 15, and the years before. We now have the freedom to work on that. And the freedom to work on that is to use beam shaping. And there are a lot of choices on the market with respect to beam shaping based in quotation marks on optical elements, but also there's combiner technology, fiber manipulation technology, and Korean beam combining, which is the most impressive stuff and for sure the most expensive stuff these days, we have to admit. Nevertheless, beam shaping is crucial, and it really helps in many, many applications, and also in the applications we are addressing in e-mobility, to increase the quality of the final weld of the final product. We have done so with our ScanMaster, which is a combination of many Precitech knowledge, from cutting to sensor technology to welding, which is all part of that ScanMaster. But the ScanMaster also includes beam shaping technology. And we have partnered with K-Labs on that, because we have seen that that technology is for us the most promising one, because it can be easily integrated into our beam path, and it can easily change from the old-fashioned just Gaussian or top hat beam profile to a better profile for these specific application. Which means for us, it's just an add-on module, which is in between the collimator and the processing head, in order to change the intensity distribution and in order to increase speed, reduce the spatter formation. So there's many, many benefits for us to include those elements, to include beam shaping in our beam path. For sure, and this is what Antonio already said, for sure, we are also taking care about the quality with means of sensor technology. So there has always been, and there will always be, Precitech products with sensors. So no Precitech processing head will leave the company without at least one sensor. And in welding, it's most probably photodiode sensors these days. And the old-fashioned way of applying photodiode sensors was to get the fingerprint of a process to calculate envelopes for the upper and lower interaction limits, and to say the process is good or bad. So we have taken the chance with customers to name one of the customers is Audi. We have taken the chance to go one step further. We have now worked on the possibility to derive specific physical information out of that process light. Customers like Audi, like others, approached us and they said, so we need more information. Just red-green is not enough. We need information about, for example, the strength of the weld, or the electrical resistance, or the depth. Okay, let's say depth we had in our pockets already by applying OCT. OCT is one of those sensor technologies which was more or less pioneered by Precitech in order to measure weld depths during processing. But this is just one of the physical information customers were talking about. If we talk about other physical information, as I said, like strength or the electrical resistance, we need to go one step further. And this is AI. We need to apply AI. We have increased our AI knowledge at Precitech by setting up a department at the University of Karlsruhe, which is the Precitech incubator. These are data scientists. They only know data science. They only know data processing. And they worked on applying specific deep learning algorithms on our time series data. And in the end, we had the other way around. In the end, we had those information, those mission functions where we could bring measurement strengths to predicted strengths in at least two applications. The one on the left is a high power application, 3.8 kilowatt aluminum welding. The one on the right is micro applications, nanosecond lasers, dissimilar materials. But in the end, it's more or less for the artificial intelligence approach, it's the same. We applied approach based on long-term short memory, LSTM, which is, as you see, one of the possibilities out of many, many in the deep learning portfolio. LSTM is maybe known from the one or the other who is listening as the deep learning algorithm behind Siri or behind Alexa. They also use LSTM. And it's one of the specific ways of working with time series data. And our photodiode signals, those are time series data. It's a lot of data, I have to admit, and it's a high frequency of data, but the LSTM is one of those which is the most promising. And in the end, our approach is to be able to work with AI algorithms on laser welding applications, to apply AI algorithms. So this is one of the applications where we're working on now. So it's different to the two which I showed you before. This here is the battery contacting, and for sure the physical value here, which is important, is the electrical resistance. You see, just for exemplarity purposes, we have shown here a zigzag welding. So customers use different strategies for welding these contacts. Nevertheless, the idea is we get the time series data, we apply AI, and in the end, we derive the electrical resistance directly in microohms out of the emission data, which is coming from the process. And you see that we can calculate good or bad resistance. And together with the customer, we have taken the chance to apply a repair weld next to the origin weld, with the hope that we then can bring the electrical resistance to the desired value. And okay, we have one customer who is doing that right now. It's just starting. So for us, it's also new technology, new experiences. But we are hoping that we convince more than that one customer on the profitability of applying AI in those applications. And maybe we can generate some kind of cloud, customer cloud, Precitech cloud, whatever the name is, that we can also connect information over the global planets. Okay, we are a small company, but nevertheless, we are globally active. And maybe we can also use that chance in order to increase the knowledge and to teach and learn our AI models just over the globe. So yes, these are the messages I hope you take home. It's an extra mile, and we go the extra mile. The extra mile is definitely with respect to AI. We can check mark that we have successfully started beam shaping inclusion in our processing devices. We can check mark that we apply AI. Nevertheless, every AI application we do right now is a whole lot of work, because the training, to get the training data, is really expensive and time consuming. Nevertheless, if we are able to convince more customers, maybe we have the chance to continue and working on that and make people happy. The typical epic question in the end, what can you do for them and what can they do for you? So we can provide knowledge on the applicability of AI methods in combination with laser processes. And we need customers who are willing to provide their data in order to make our work easier, in order to speed up the AI applicability in lasers. Customers just need to be open for the new technologies, and if they are open, we increase the speed in that innovation. Thank you so much for your attention.
Thank you very much, Marcus, for a great presentation and for let us know more about the use of AI. We have time for questions, so you can raise your hand. You have the button in the bottom of the page and make your question directly to Marcus. I will perhaps start with a question is, for the moment, I guess it's more a task of Precitech to generate data regarding AI, to generate data to get the confidence of the customers, to help them to understand that this is going to help you, or this is already a common effort that you need their help to produce data and to improve the amount of data that you can use to improve the quality of the results?
So if we partner with a customer, it's quite easy. So because we are quite open to the customer that it takes some time to be ready, to be industry ready. So it's not done in 1 week, but they see the benefit. We can show the benefits because it's not only these 2 applications we have in our pockets. There are more, but I cannot disclose everything. Nevertheless, we see that there is some discussions on the position of customers being willing to share their data to others. And we need to find at least, let's say, one level of confidentiality, which we can guarantee to customers. And above that level, maybe information can be used not only for us, maybe for the community in order to speed up those processes. But it's a new thing. People protect their data, and I'm pretty sure it will be at least the next 2 or 3 years that people protect their data. But at one point we see and they see that it's beneficial for the community in order to share at least to one level. It's not really confidential data we need for training the AI network.
Okay. And another question is about the limitations. Is there any limitation, or do you see any limitation depending on the type of laser, material, the task, or can be applied, let's say, anywhere?
For sure. But in the end, it's the better the process is, the most robust the process window is, the easier it is also for the AI to find those physical values or that information the customer is asking for. So if you have a high fluctuating process, and if it's really hard for you to process or to generate quality, AI is not it's not Harry Potter in the end.
Very good. I don't know if there is any other question for Marcus. Feel free to raise your hand. Well, if not, thank you again, Marcus. You can perhaps type your email address in the webinar chat so people can reach.
I'm here for the rest of the
okay
evening.
Okay, so you can interact with the people if there is any.
Yes.
I see a question from Enrico Casamenti in the chat. I don't know, Enrico, you can do the question directly.
Oh, how often do you double check the results with your predictive model? Yes, right now we have to do it actually, because we are still in applications where most probably also the process input parameters are changed. Oh, I'm in an open space.
Yeah, he cannot make the question directly. So he was the question about how often do you double check the results with the predict?
But he can hear me. I hope he can hear me.
Yeah, he can hear.
Okay, so that's okay. So as I said, we have to double check the results because we are in applications where still the process input parameters are changed. That's why we have to double check, because we have, when we started, we have been of the opinion that we need to fix everything, fully fix everything, but we have seen that there's some space in between. So it's not that strict, but for sure, if you change, let's say, dramatically the process input parameters, we have to. The double check will result in maybe a new slight training of the model. I
Very
hope
good.
that is enough,
Yeah.
but nevertheless, so if you need more information, just send me an email and we can discuss that.
Perfect. So thank you very much again, Marcus, for the great presentation.
You're welcome. You're welcome. Thank you. Thank you for having the chance.
So we can move now to the next speaker, and it's a pleasure to introduce you, Xavier Beder. He's the head of Dynamics and Control at IDECO Research Center, and he's going to present their work in laser blanking for the automotive industry. So Xavier, the floor is yours. You can share your screen.
Okay, so thank you very much for the introduction. So as you said, I'm Xavier Beder from IDECO. It's a research center in Spain. I'm more focused to machine tools in general, but laser cuttings for me is new, but it's very interesting for the fact that we need special machine designs for that. And we are working on that. Sorry, I will share my screen. So I hope you can properly see the screen.
Yeah, everything good, Xavier.
Thank you. So yes, as you said, for laser blanking applications in the automotive industry. So it's a project that is funded by the European Union, and we're working on these laser blanking applications. So the objective of the laser web project is to be able to go faster with the laser technology and to be able to replace the standard solutions. So as you will see for laser blanking, it will be in competition with mechanical press blanking. And for that, we need to work on the different aspects of the process. So the process itself, but also the machine design and the programming and program optimizations to be able to go faster and to be more productive with the laser technologies. So in laser blanking, we are competing against the mechanical press blanking. As you can see here, there is a coil of material, and with one stroke of the press, we can produce one side panel of a car. This kind of process is very productive because the stroke rate of the machine is very high, but has little flexibility. So the objective that we have is to replace or complement the current technology, that is the mechanical press, with laser blanking technology that is much more flexible. We can easily change the shape of the parts, whereas with the mechanical press, we will need to rework on the toolings. The setup is quite fast also, and we can program all the elements, and so we don't need specific toolings for each part geometry. And we can also optimize the use of material from the coil because we can have better nesting of the part geometries inside of this coil. The main drawback of the laser blanking compared to the mechanical press blanking is the productivity. So the idea is not to replace all the presses by lasers, but to combine both technology to keep the press blanking for high batch and large volume production, and to use the laser solution for medium to low production bytes, and when we need this flexibility to be able to change from one part to the other one very rapidly during the day. So the laser blanking line, it's composed of different elements. First, the coiler, that is taking the coils and bringing it to the leveler. The leveler will make it flat, and then we will have a small loop before to enter in the laser cutting. If we compare to classical press blanking, usually this loop is much bigger and requires pits or civil work because we need much more buffer of material before the presses. With laser blanking, we can have lighter solutions with a smaller loop before this laser cutting process. And then we need a stacker that should also be a flexible solution because we want a complete line to be flexible so that we can change easily the production from one batch to the other one. And so we need also a stacker that is either a robot or a robotic solution to adapt to the blank geometries. You can see here a small video of what is a laser blanking process. So you see the laser cutting head that is cutting on top of an open hole so that the sparks can go down, and the coil is moving while the cut is being performed. So this is quite different from the classical format cutting machines, you see that we do not have those slats to support the part, but we have one band that is required to be able to move the material and the portions that are already cut within the skeleton of the coil. And you can see also in the videos that we have two laser cutting heads cutting at the same time on the same moving coil. And so here you can see at the end of the line the skeleton and the parts that were taken from the skeleton. So compared to the classical cutting process, we have programming challenges because of these moving coils and the fact that more than one cutting head is cutting at the same time on the same parts. And to increase productivity, one solution can be simply to increase the number of cutting heads that can process the material on the coil. So this is one solution, but it also reaches its limit because when we have 2 or up to 3 laser cutting heads, then it's difficult to keep the balance between the working heads and to have them turned on all the time. Maybe one laser head will be waiting for the other ones. So within this European project, that is the LaserWay project, what we aim is to develop new technologies to be able to have faster machines, so to have high accelerations, and we are targeting 6G of acceleration. And we can achieve this thanks to new innovative kinematic design and also the use of lightweight materials with composite fiber for all the moving parts, so that we can have a strong architecture with lightweights. We're also implementing online vibration minimization techniques because in this process, the main issues are coming from the vibrations that are disturbing the cutting process, and also offline optimizations, as we have quite a lot of freedom in the path planning and work repartition between the heads, and this can be used to first optimize the repartition between heads, and also to smooth the trajectories so that less mechanical strength is applied to the machine due to the tool path. Then we are also working with the process, and Precitech and Marcus is a partner of the European project. And in that sense, we are working in the gap control. That is more difficult in this kind of application because the sheet is moving. We have motions also below it, so that we tend to generate vibrations. And we can also have internal strengths of the coils that are released during the cut. So we also need automatic detection of cut loss and sensors integrated in the cutting heads, as commented before, to be able to have online process monitoring. And then the idea is to have a stronger process with more resilience, because in general, the parts are not that expensive as a unit part. But what is expensive is to stop the complete production line because of one loss of cut, for example. So what is important in our mind is to be able to detect those failures in the process and to discard those parts without stopping the complete production line. And the end of the European project will be for 2026. So we plan to have new machine design by that time. So this project is carried out by a large consortium where 16 partners. We have 3 different technologies, but for the partners that are working with the laser blanking technology, we have in Spain, so IDECO is a research center, and we are the main coordinator of this European project. Then Fagor Sate is a large player in the automotive industry, coming from the mechanical press sector and now implementing these laser cutting solutions also. The machines are controlled by the CNC from Fagor Automation, so that we have enhanced both the mechanical design of the machine and also the CNC controls that is adapted for those specific laser blanking challenges. Then in Germany, so Precitech is provider of the laser cutting heads and all the sensors and monitoring systems. We are working with ModelWorks that is performing optimizations of the toolpath geometry and nesting. And finally, in Czech Republic, with Compotex, that is a provider of carbon composite structures that is helping in optimizing the design so that we can have these lightweight solutions and reach higher acceleration speeds. So to conclude, in this European project, we have 3 main technologies. You have seen some information about the laser blanking. We are also working in micro drilling and ELA processes. All of them have the same characteristics of productivity, very high speeds, where we need to work on the different aspects, process, design, and optimization of the program to be able to reach this high productivity and replace more classical processes like the mechanical press blanking for this presentation of today. So thank you for your attention, and I will be pleased to answer some questions.
Thank you very much, Xavier. We have time for questions. So raise your hand or make your questions in the chat. I have a first question about you mentioned the minimization of the vibrations. Could you talk a little bit more about the process that you are implementing? Is something that you are including some kind of air type of vibration isolation?
Yeah, so for the first aspect for that is coming from the machine design. So we are making mechatronic simulations where we take into account the machine architecture. We know the moving mass, and we can design the machine so that we can reach those high accelerations without having large overshoots and vibrations coming from the mass of the moving heads that we are moving at high accelerations. So this is the first step in the design phase, and then during the implementation, what we have is that as we are integrating also the CNC provider, we can slightly change the set points that are sent to the machine so that we can avoid exciting the mechanical frequencies of the machine tool, and like this we can reduce vibrations. So with online solutions also based on filtering techniques.
Okay. And what's the answer from the end users? Let's say you mentioned that is not a technique or a technology to replace completely the traditional one, also due to these issues with the productivity. So do you see that there is a good potential to enter in the industry as a complement? Do you still see some drawbacks that you need to solve?
So of course, the final user would like to have high flexibility and high productivity at the same time.
Yes.
But they need to choose. But so it's clear that now the situation is quite good for these laser blanking solutions because it offers this flexibility that is not present at all with the mechanical blanking. So the main customers will combine both. For the large batch, they will go with press blanking because this is the right solution. But for service centers or to make sure that they will not disturb the complete production lines because they have some issues in one blanking line, they would have these side lines of laser blanking that are very flexible, and that will help to generate buffers of parts when press blanking has a downtime, for example.
Okay.
So those technologies are not really competing, but they are complementary.
Yep. We have also a couple of questions in the chat. The first one is from Enrico from Fentoprint. Is there any specific reason why you are not considering laser scanners to increase the speed?
So that's a good point. The typical workspace is like the width of the coil is 2.1 meter, and the workspace length is 1.5 meter. So the working array is quite large, and that's why the typical solution is to move the laser heads. That in this case is from Precitech. So for smaller works, for volume, maybe a scanner could be interesting, but for large volumes, I don't have any solution in mind.
And we have another question from Juan from Exxon Engineering. Do you think that the focus shift with higher laser powers might affect the reliability of the process?
Yes, so this focus shift, so we are thinking about gap control to maintain the gap between the coil and the laser head. So this is something that is clearly affecting the process. And we have residual stresses that are relieved when we are cutting the material. So we are working in having higher dynamics in the measurements with the capacitive sensor that is integrated in the head, then the control loops to close faster the control loop, and also to have higher bandwidths of the feed drives in the vertical direction that is controlling the gap so that we can withstand more perturbations and still keep the gap in the good process window so that we can have nice cuts even with larger vibrations.
Just Just a quick point on that. We are currently working on cutting heads which can stand 150 kilowatts. So we are quite aware of any kind of focus shift with transmissive optics these days. And whenever we see the need for applying also AI technologies, which we have in cutting heads as well, where we use AI to compensate for the focus shift, we do that. And this funded project LaserWay will be one of those where we actually find out any kind of advantages for our strategies to compensate focus shifts.
Good. So if there is no more questions, thank you again, Xavier, for being here this afternoon, and thank you for the presentation, and good luck with the project, and we hope you the best for the final results.
Thank you very much.
And we can move to our next speaker. So yeah, let's talk about CO2 lasers, and it's a pleasure to introduce you Christian Dini, commercial manager at the company Luxinar, and he's going to present how CO2 lasers can contribute to the manufacturing of batteries. So Christian, the floor is yours.
Thank you, Antonio. Thank you for the invitation and the kind intro. Let me quickly share my screen here.
Remember the last one you tried, that was the one working.
And it's a challenge again, because I have now 3 that look similar. So let's try and error. Let's see what it does. How is it about it? Can you see?
This one is starting sharing, so it looks good.
Okay.
Yeah, we see the screen. Thank you.
Excellent. Lucky me. Okay. Maybe a word up front. This is a reduced presentation, so because of the time frame, I did hide a couple of slides which are included in the presentation that I sent you over in a PDF format. So whoever is interested in the details behind it, they are there, but I can't really go through all the slides here in this presentation, time constraint reasons. So off we go. Just a quick word. Luxinar is 25 years old, but in the past it was known as Rofincina. And the latest changes here are not even on the slide, but we got acquired by Tro Group, and we are now teaming up with Irradian Group. And so there is now a joint product envelope starting really from 30 watt. And we are kicking in at 100 watt CO2 power, going up to all the way up to 1 kilowatt. And we also have ultra short pulse lasers currently up to 160 watt. And again, same thing, Irradian, they have a lower power range. So this is actually matching quite nicely. But right now, this presentation is really about Luxinar. And yeah, we have presence around the globe, and an installed base, which is actually not an accurate number here, which is way over 30,000 lasers as we speak. But now let's go right into it. Where do we play to our strengths in battery manufacturing? Of course, there's the applications of the ultra short pulse lasers, but other than that, there is everything where you have organic materials, where you have foils, whatever kind of foils, or even the organic liquid that's in the battery. But I have brought 2 examples here, but here you see a quick rundown on different applications. This is cutting of ceramic coated separate foil on the right hand side of the screen. The left is actually the ultra short pulse notching and slitting of the electrodes. Same thing again, we have on the left hand the LXR series doing surface texturization. On the right hand side, we have another application where we basically decode a battery, and that's the second application we're going to talk today. And finally, we have wiring, we have hairpins, we have bus bars, and we have filler ports. So that's basically all applications where CO2 lasers can be used. obviously hairpins and bus bars. There's, let's say, quite a bit of conversation. Let's say there's a challenge between this and fiber lasers, but it's a common application to us. So why use CO2 lasers for batteries in general? There's a lot of organic materials present, which I already mentioned, and there's different wavelengths available for those CO2 lasers that interact with different plastic materials. Those lasers are, I mean, they are really mature technology, and so the level of maintenance for these lasers is minimum. Actually, the lasers themselves are maintenance free. You typically have to care more about optical beam paths than about the laser. This laser technology, also it's a gas laser with a sealed gas chamber, the service life is quite long. So we see anything between 30 and 50,000 hours of lasers being in operation, in continued operation. And if you compare it to today's pump diodes and seed lasers, that's quite an impressive number. So this is long lifetime. Also, it's not solid state. It easily competes and compares to solid state technology. And finally, once there's a refurbishment required, the cost of that is very low because you typically need a few optics and a new gas fill, and that doesn't compare anywhere near to if you need a new set of pump diodes. So this is basically a very economical technology. Now jumping directly into the two examples, not limited to the two, but the two I chose for today, which is the separator foils and unwrapping of batteries of prismatic cells. So the separator foils, most of the time today, they are still mechanically cut, but with the introduction of ceramic coated separator foils, there's a major issue with that because first, ceramic introduces a new level of wear to the knives, but there's also, and more importantly, there's the dust contamination of chipped off ceramic parts. So if you move to laser, then you have a non-contact, no wear process here. And the advantage of the CO2 laser over the ultra short pulse laser in that case is simply, again, what we had to review before. It's the low cost and the simplicity. Even if we talk about laser safety, I mean, you need just acrylic or some kind of polycarbonate housing, and you're done with a CO2 laser. So that means this is basically the two levels where it really excels. It is easy to use, and it is improving the economy because it's lower cost. So what we did here this time is we tried to compare 3 different wavelengths on 3 different materials. And in order to compare that, we created an environment where we have same power and, let's say, very similar spot size, not exactly the same, but very similar. So we tried to create a condition where we really have comparable data between 3 wavelengths for 3 different, very typical separator foil materials. And those materials are, yeah, now you basically feel what, so a few slides are missing, but this material 1 is a material where there is a ceramic coating applied. Material 2 and 3 are PE foils, but they are not clean PE. There is a slight part of polypropylene present, and that makes it so interesting for the 1025. But anyway, what all our examples show is that we get at least as good or much better cutting performance with 10.25 microns. So this is something I recommend everybody to look into if he is thinking about coming up with a cutting station, a laser-based, CO2 laser-based cutting station for separator foils. And in this case, the 1025 really, that translates in not only the higher productivity, but you basically get up to 3 times out of, actually even 4 times depending on the material, out of the same production line if the laser would have been the bottleneck before, if you used 10.6 or 9.3. And at the same time, so you simply, the same cutting process is requiring less energy. So the carbon footprint of that particular process can be improved by simply using a laser wavelength that interacts more efficiently, more effectively with the material. So just a quick wrap up for this application. So we basically saw that the CO2 laser is a reliable tool, easy to integrate in that kind of application, very economic. There is a discussion, or let's say one argument typically is, okay, but solid state lasers have a better wall power efficiency, wall plug efficiency, but it's not what makes the process efficient. Efficiency is how much power do I put in versus the cutting speed. So if my wavelength is more effective than on the material and I can speed up the process there, then it's the overall efficiency that I need to look into, not just the electrical wall plug power. Those lasers have definitely a lower cost of ownership and simple operation. And by the way, since we are discussing this in Europe, I know from firsthand that this is basically already a standard in Asia. So there, the distribution of CO2 lasers within that battery manufacturing facilities and processes is basically much more developed than over here. So little challenge to the European battery manufacturers. Look at this and work with us so we can catch up with what in Asia is already going on. The second process I wanted to show you today is unwrapping of batteries. Why would somebody want to unwrap a battery? We have 2 scenarios here. One is yield issues of production of battery production, where it's going as bad as up to 30% rejects. And even if that number will come down over time with the growing number of batteries used in the field and coming to an end of life, even after their second life, the demand for recycling will grow. So currently, this is a purely manual process. So that it's really people sitting there with knives, spatulas, scraping and scratching, and then using very aggressive solvents to wipe off the stuff. It's definitely not a process that anybody really wants to do, but this needs to be done. So we can introduce basically an automated process here that does not apply any force to the material, to the thin wall cell housing, and it's creating very repetitive results, and it's basically avoiding dense scratches or any deformation of the battery, of the canister, because that will be reused. Reused if it's from non-conforming cells out of production, and recycled, of course, if it's basically dead batteries after use. The other thing, as we already mentioned, is the change from very aggressive chemicals that are not only aggressive to the user and the environment, but they're also an issue in the when you basically need to dispose them, or not really recycle them, but you need to get rid of them. Let's say it that way. So there's twofold. So it's basically more user-friendly process, and it's a more environmentally friendly process. Not to say that there is not issues, because you evaporate a lot of material, but the key technology here really is it's it's a delicate process, because if you're working on ready-built batteries and you need to unwrap them and you want to reuse them and rework them, then you need to manage the temperature, because if you heat up the battery more than 80 degrees, then the battery is damaged. So the goal is to have, let's say, the same productivity of a machine that the workers, the people have, but with less environmentally unfriendly materials, more protective to the battery itself, and basically not damaging the inside of the battery. And that all was achieved. We have there a slide. We always do spectrum analytics of the materials, and that is why we say contrary to the expectations, you see this plastic wrapping would have had a much better absorption, very little absorption anyway, but much better in 9.3 than 10.6. But in the end, that's always one of these surprises. The ablation rate of the 10.6 was simply more efficient and better, so we went with 10.6 here. So yeah, this is basically the outcome. We were near the we were slightly in the low 60s in centigrade, so the cell was very safe, and it was no problem. The productivity was very comparable to the hand scraping, and the power level we used was actually a 450 watt laser here. And the one thing that doesn't work, you don't get a totally clean surface with CO2. There was a very, very thin sticky residue left, but that was easily wiped off with a little bit of isopropanol, so a very mild solvent compared to what they typically use. And that could be also fully automated. So this whole thing, from removing the wrap to removing the residue, could be an automated process. So what's the conclusion then of this process? We can create a more environmentally friendly, I would not call it a very environmentally friendly process, but a less environmentally harming process. Definitely much better for operators. That's definitely a major improvement, and it will give you repeatable results and basically avoid more rejects because of mechanical forces and tools are basically applied. Definitely one thing is the fume extraction. You evaporate all this, so you have to make sure you have a good fume extraction and adequate filtering. So basically that remains of the process will accommodate in that filtering. Then there's let's say a finishing process left, but in the end, the total process is much more beneficial compared to what is done today. And with the growing demand of batteries, even if the yield improves, there will be always batteries right out of production that need to be reworked. So this is then a measurable and a controlled process to basically cycle those back into production. And then, we are here with the epic questions. Well, what can we do for you? We refer to a database of about 3,000 different applications. And if you have questions about can it be done, what is required, I think it would be a good step just to see if we have something already, or if not, then we will do application or process development work with you. And that also is funneled in a long experience of system layout, how to basically make that laser work in sense which beam delivery, what beam steering. So we can basically guide you the way to a laser machine or help you with the selection of a laser integrator that will build basically the best possible machine. What can you do for us? Well, of course, speak to us. Whenever you see organic materials, then please think about the good old CO2 technology. It's old but good, and it's still out there and needed. So yeah, we would be happy to talk to you. And with this, thank you very much for your attention, and I'm here for your questions.
Thank you, Christian. So we have time for questions for Christian. I could start with one, because you mentioned that in Asia this use of CO2 lasers is more normal, let's say. But do you think it's due to the lack also of battery factories here in Europe, or is because we are in Europe thinking in other technologies that could be more useful for the battery manufacturing?
Ooh, I think it's a bit of a philosophical question. On the one hand, obviously they have huge capacity in production, and they move on very fast. So I think it's they're probably less afraid of trying things, and maybe also don't try to understand everything to the very very last detail. But if it works for them. So that's and that's basically also, how should I say, one of the key takeaways that I have. So whilst the conversations I have with local customers, it's more looking into this and researching for it and trying it out in the future. And over there, it's common. It's basically everyday production technology. So these days, maybe we need to start learning from Asia, or at least get inspired. But yeah, if I look at the commonality, then it's a huge discrepancy between how many lasers are going into this application here in Europe compared to in Asia.
Yeah. Well, thank you. Thank you for the answer. I don't know if there is any other question for Christian. If not, thank you again. Thank you very much. And
Thank you very much.
That you have this solution also for organic materials. So we have it in mind.
It's a wide envelope, and yeah.
Good.
Thank you very much.
Thank you, Christian. So we can move to our next speaker. So it's a pleasure for me to introduce Germán Vergara. He's the CTO of the company New Infrared Technologies. And yeah, he's going to present the high-speed monitoring of the brake disc coating process. So Germán, thank you for being here after all the troubles with the connection. I think you're still muted. You can just move in the bottom left. You can remove the muted.
Can you hear me now?
Yeah, we can hear you, Germán. Thank you.
Thank you very much, Antonio, for inviting me to give you this presentation, and let me to introduce NIT. NIT is a company based in Madrid, and we produce infrared sensor and system dedicated to monitor industrial processes. We have a good experience in laser. I'm here for speaking about a specific application, which is high-speed monitoring of brake disc coating processes. Just let me to start with a small introduction about the problem. The motivation of that is big part of the contamination particles coming from a car is coming from the brake disc. And European Commission thinks that there is technology enough for avoiding it, and it is the reason because they approve like some month ago the new Euro 7 standard that will demand significant reduction in the emitted fine dust particulate by gas emitted by these brakes. It seems that the industry has to work because they had to reduce the particles coming from the brake disc, and the solution that they reached was to apply a thin layer on top of the brake discs. Basically, there are a couple of 3 layers of that, and they look for the right technique for doing that. And finally, it seems that there is consensus in the industry that this coating has to be applied by high-speed LMD, laser metal deposition. The reason is because the coatings produced by high-speed LMD provides a long and effective protection of emitting a very reduced number of fine particles, and they are compatible with Euro 7 requirements. It is a laser-based process, and this is the reason because the industry start to work in this matter. They try a lot of alloys. Most of the people use titanium based alloys for doing that, and laser. The challenge for the industry is to reach volume production, because brake disc is millions of units per year, and it means that they need a repetitive and reliable process. Don't forget that they are using many very high power, more, in some cases more than 20 kilowatts. It seems that they have to find the good and repeatable process for doing that. And this is the reason because most of them had decided to use monitoring in real-time monitoring system. And this is the reason because I'm here. Okay, just as you know, NIT has a big experience, a long experience in monitoring laser-based processes. We have the system called Clamid, that is well known by the industry for controlling real-time laser metal deposition. Based on our experience in monitoring laser-based processes, we have developed a new solution for monitoring in real-time high-speed LMD process for coating brake discs. The solution is commercially called Discover IR Suite, and let me to do a brief introduction about this product. Okay, as you know, our infrared cameras, they imagine the melt pool. The melt pool is basically the result of the interaction of two main actors in the process, the laser and the powder. And this is because we think that imaging the melt pool is one of the best techniques that you can use for monitoring a laser-based processes. This is very important that the technique that you use for monitoring provide you useful information on the process. Otherwise, you are trashing the time. You can see here image of a brake disc and also the image that we can reconstruct using melt pool. And if you see in detail, we are able to reproduce with a good resolution practically all defects in the disc. Now our challenge is to make or to develop automatic recognition of this type of defect. The problem is here we are more or less we have a good system for LMD. LMD, all the powder is melted on the substrate, and we obtain here is a very sharp image of the melt pool, and we can imagine it. Don't forget that we are imagining like 1,000 frames per second. We take 1,000 pictures of the melt pool per second, and we extract some information. But in case of high-speed LMD, something is different, because the powder is melted above the substrate. As a result, the image that we obtain is like a it's like a blue melt pool. We have to make an assessment of the process just only analyzing the information of this blue image of the melt pool. And we did that. I mean, we I'm not going to go into details, but we obtain 1,000 pictures like this per second, and we extract information about that just for being sure that the process is going well or not. How we do that? As I told you, we develop a Discover suite, and it is specifically designed for high speed R&D for break this coating process. That we do is to analyze every picture, and we extract almost more than 40 features of the picture. What is a feature? Feature will be intensities, centroids, areas. I mean, we have a lot of mathematics of each picture, and we extract information of them. The system has to be very fast. We try to do that. This is basically the part of the system. We have three different parts. This is the Discover camera, or this is the hardware, and then we have the software. The software is divided or split into different software. The Discover production software, what we call HMI, and we have a Discover analysis software, which is used offline, just for defining profiles. The hardware is the sensor chip has double bus for faster data transfer. You have to think that we have to be very fast. It has a Ethernet connector because we have to transmit a lot of data. We have a cooling water for making the sensor stabilize the sensor temperature of the sensor, and optics that it is specifically designed for every custom. The firmware has also data transfer rate increase, the internal processing on system on chip, and FPGA plus IRM, and also we are now working in the PLC communication for numeric schemes. The matching interface looks like it appears in the screen. It has two areas. The right area is dedicated to the sensor, and the left area is dedicated to the assessment. This with this HMI, we can obtain process videos and then analyze them, and then to use them as profiler. The analysis is a very complex software. As I told you, we start 40 features from the videos, and analyze them and compare with other processes. Finally, we are able to define the profile that we have to load on the HMI. And the assessment maybe is the most important part, I think. Finally, that we have to do is to say to the operator if the process was or not. It is maybe the most important part of the process. This is the more difficult part of this system. And right now we are really happy with the result that we have obtained, because our system has been installed in production yet. Just to remind you that basically Discover is a data killer. I mean, we are starting, if don't forget that we are starting of multiple image, 1,000 multiple image per second. And the image are 64 by 64 pixels, a low resolution image, but the final the amount of data that we have to process is around 66 megabytes. That we do in Discover is to kill, or basically to extract all the information, because the end of this process is just to provide 2 bytes, or not. Okay. This is basically the main advantage of uses the Discover IR suite to extract the right information in real time. You have here some examples, but I'm not going to go deeper. Another and the last point that we would like to remark is we have to advance toward automation. Don't forget that maybe high-speed LMD for radix will be one of the first laser weld process that will be employed in volume. I mean, 24 hours, 360 days, 24 hours, 7 days a week. It means that the sensor will be a key parameter for doing that. It will be necessary to put all the sensors in the same network. I think Marcus has spoken about the importance of the data, the data analysis, and I think Discover IRC will be a process system which will be part of the industry, on the industrial process. Here, this is here is the Discover that data that we have. Actually, the HMI will be record videos, area chart, this map and report, and finally the machine to machine will have two different well-defined areas. One of them will be connected by OPC UA for data access and very important performance that will have Profinet real-time class 1. I mean, I think we are ready for being installed in the industry right now. In conclusion, that the new Euro 7 standard will demand a significant reduction of the methane fine dust particles by car. High-speed LND is the solution that most of the industry has adopted. In regard of industrialization power production, the economic advantage of high-speed LMD is huge compared to other technologies, and it will be necessary to implement high-speed MWD imaging for real-time monitoring of this process. We think that Discover RUC is today an excellent production and research and development tool for quality assurance and setting up high-speed LND braid coating process. I think basically this is all I can say today.
Thank you very much, Herman, for the presentation today. We have time for questions. I can start with a question about the information that you can give to the customer, because you talk about the profiles of the coatings, but you are also detecting defects, the variation in the shapes, which is the information that you obtain from the images.
Okay, thank you. It's a good question. Basically, that the manufacturer has to define a base process. I mean, that we call profile. I mean, profile is a process that provides right coatings. If some deviation is coming from this process, the Discover IR suite will detect this deviation and also will classify the deviation.
Mm-hmm.
Yes. It is possible to do that. I don't know if this is your question. Yes.
Yeah. And is there any information in the thickness, perhaps variation in temperature, or for my understanding, you are looking at the surface, but I just want to ask you if you can do something in the thickness.
Yeah, we don't provide thickness of the process. The information that we provide is coming from the melt pool, only the melt pool. I know that there are some manufacturers that are implementing both thickness and melt pool imaging. It is a strategy that some manufacturers are now working on.
Okay, very good. So I don't know if there is any other question for Germán. If not, thank you. Thank you again for the nice presentation and for showing us your technology today, Germán.
Thank you.
So we can move to our next speaker, and it's a pleasure to introduce you, Mr. Andreas Heider from the Joining and Laser Material Processing at Robert Bosch. And he's going to present the laser technology in e-mobility applications with new opportunities and challenges. So Andreas, thank you for being here, and the floor is yours.
Thank you. Hopefully you can see my screen.
It's starting to share, so we will have it soon.
So thanks for the invitation. Yeah, I want to talk about opportunities and the challenges for laser technologies in e-mobility applications. Especially, I want to give some hints and some things we have to keep in mind to consider if we're thinking about laser technology for e-mobility, especially for high mass production. So the motivation is quite obvious. The motivation for laser-based manufacturing is mainly driven by the trends and the global demand for sustainable mobility. Yeah, this is rising and rising, and we as Bosch, we for sure we focus on these demands. We spent in 2022 above 800 million euros in electrified mobility in some production lines. And therefore, we now reached up over 5 million vehicles with Bosch powertrain components. For us, it's quite important to have a sustainable, have some sustainable solutions. So, for example, we want to increase the range for you all. We want to have a sustainable production. We also focus on the infrastructure. And for sure, on the cost itself, we want to have all the parts and the things afterwards very cheap, that we all can buy it. And this all with a worldwide CO2 neutral production since 2020. This is quite important for us. And with this motivation, we develop components as well as products for the entire mobility sector, as you can see here on the left-hand side. So starting from the e-bikes to scooters for the passenger cars and trucks and so on. So we have the whole entire mobility sector with our products and components. And on the other hand, our products and technology are represented in the complete and the whole integration level and the whole vehicle classes. So starting with very thin and small parts with the semiconductors, over the subcomponents like power modules or stators, rotors, to components, the whole engine, the e-drive, and we end up in complete integrated solutions for our customers in combination with energy storage and conversion like batteries and fuel cells. And I think you all know that if we want to have such innovative products and if we want to develop and produce them, we have to have innovative technologies for a flexible and robust and cost-efficient production. This is very, very important, and we think that the laser is one of the key factors and one of the key tools to do so and to gain this this productivity and the cost-efficient productivity. So we have the very innovative products, for example, the batteries, the fuel cells, which increases in complexity and which increases in functionality, the power electronics and e-drives, and we have to need the suitable tool for producing them. The laser is one good tool. I think you all noticed the laser is the enabler technology for new product features, for innovative products. It's very high productive technology. It's flexible, automotive, and has a very low energy consumption. So overall, the laser is very cost efficient. So why not use this for mass production? And there are some challenges to handle. And this challenge can be easily explained just by a few simple calculations for which I want to take you to small deep dives. So if we just take a look at the changeover from the conventional powertrain to the e-powertrain, so from more like steel parts to copper parts, not all copper parts, but in most of the cases. And if we just have a look to the requirements on, for example, the welds, and then we have, for example, we came from the thickness of the parts from the conventional powertrain, we came from 300 microns to roughly about 1 millimeter in thickness. This was always for injection pumps or for Bosch products, for high pressure pumps. And now we end up with a very, very increased range of requirements for the thickness where we have to fulfill. So we are from 10 microns for the battery foils, for example, and we end up, in this case, for copper, to weld copper 5 millimeter thickness, which is really challenging using the lasers. So, for example, for busbar welding for e-drives. And this increased requirements, this increased complexity will be much more pronounced if we have a look at the welds per part. So if we came from 1 to 20 welds per part, for example, for the high pressure pumps, then we end now in 1 to about 8 or 600 welds per part. And these welds are all responsible for the functionality of the product. And if one weld is missing, if just one weld is missing or has a failure, the whole part can be destroyed. And this is quite important to know, that we cannot throw the parts away because they are also extremely expensive nowadays. So we have to consider that this complexity of these new products, of these new materials, are extremely growing, and we do have to think about new strategies, new system technologies like the laser technology for a robust welding process. Otherwise, we have not a cost-efficient production. And just another simple calculation to show you how important it is to know the process chain, and to consider all the things around the laser. Is done with a rough estimation by producing fuel cells, for example, the bipolar plates. And if we just calculate the production of some bipolar plates, so we have, for example, 150 to 250 millimeters in square of the bipolar plates, then we end up with a sealing length, so a welding length, if we're using the laser, for 1.2 meter. And if we assume that such one bipolar plate has an output power of roughly 320 watts per bipolar plate, and we want to end up with, for example, 100 kilowatts fuel cell stack, then we have to weld 384 meters in laser welds, and all the laser lengths should be reliable and for sure tight over lifetime for the fuel cell stack. And if you go a step further, if we assume we want to have 1 million cars per year, for example, with 1.4% of cars which have a fuel cell inside, then we have to have a weld length of 384,000 kilometers a year. And this is exactly the distance from the Earth to the Moon. So I think these numbers show quite easy that we have to know about our process. We have to know about our tool, our laser in this case. If you imagine that we're using a 50 micron focal diameter, for example, 100 micron, and have to weld defect-free about 300,000 kilometers a year, this is quite challenging. And this we have to keep in mind. And another example is if we weld copper. Copper is quite challenging at laser welding. And we do have to weld copper if we're talking about production of e-drives. So production of hairpins, for example, or stator. We have this light blue requirements here. We have spatter formation, we have melt ejection, pores if you do not use the right parameters. We have a high heat input, we have a variation in penetration depth. And what we do have too is we have to consider the whole process chain. So the requirements from the process chain, so the product geometry, the environment, accumulation of some defects, tolerances, and so on. So it's not anymore only developing the weld itself. So we have to consider the whole process chain. So it's not sufficient to take only the weld into account. So we have to take into account that we have relevancing, influencing factors, effects. We have to understood the whole process, and we have to understood the influencing factors and the physics behind the cause-effect relations. Then we gain and end up with a high efficient production. Also, one easy example is if you want to weld such stator production for eDrive. There is not only 1 or 2 or 100 welds where you have in the lab with totally perfect condition. In production, at the very first beginning, you have this perfect condition, but for a production line which runs over several years, you have some issues, for example, with the process chain, with contamination from parts you will buy from suppliers, from the process chain itself. In this case, there's quite an easy example. If you have the stripping process from eDrives, if the stripping process for copper wires in before of the weld, and just one simple wire has a pure stripping qualities or acetyl layer from this isolation is still on your wire, and you want to weld this, then you end up with this high-speed image which you can see here. So you end up with a really huge pore formation, which you cannot see after welds, which you cannot see with visible inspection. So you have to know about the process. You have to consider the process chain. You have to consider the interaction between some contamination, some other effects for a stable welding process. So it's not enough to look at the lab. You have to also take into account the whole process chain. And therefore, you have to know and have to have a deep understanding and have to know the influencing factors of the whole process chain. And this will become very important for mass production, especially for the e-mobility selection. So just want to show you some examples that we have to face on if you do mass production. And just a short summary, I think there is a global demand for sustainable mobility, and this is rising and rising. And we, as Bosch, we offer innovative products and technologies where we face on this complex, this complex process chains, these complex processes. And I personally, and we think that the laser technology is one key factor for today and future's electrified mobility. There is no single fuel cell, no single battery, no power electronics, no eDrive without even one laser technology. So we need the laser to be very fast, to be good, to be sustainable. But therefore, we have to know about the process fundamentals. We have to know about deep technologically basics, the basic understanding, and then we have to transfer this. This is quite challenging, but I think we're on a good way. There is still a great demand for novel laser technology, is still rising. We have innovative solutions. So I think together, laser technology has a great potential, and we can make the future, the future with sustainable mobility if we transfer this technology USP from the laser to real products. Well, thank you. Hopefully, I can give you a short overview of the challenges in e-mobility. Thanks.
Thank you very much, Andreas. Thank you very much for the nice presentation and summary of the challenges. So we have time now for questions to Andreas. I can perhaps start with a question about you mentioned that you are sure that you need or we need the laser technologies. But do you see any trend in using any particular technologies, or do you see that we have a presentation from Luxinar about CO2, but also ultra-fast laser are being used? How do you see the map? Is there room for everybody? Is there any technology that would be more prominent than the other?
I think there's no rule for everyone who can say you have to use this single kind of laser for everything. So if we're talking about the wavelengths, especially for copper, green or blue lasers are very good for a niche. That's very good. There's a niche where infrared laser cannot handle some problems for small thin parts, for thin foils, for example. There's blue laser very good, but they are not the overall thing for all the copper welds. I think a trend which is very, very good is beam shaping, static or dynamic, so temporally or spatially. So we're having all this spot and ring combination from all the suppliers, which is very good, has very robust processes. We increase the process robustness, especially, for example, for contamination. We have to use such things. I think spatial and temporal beam shaping, like we see this Sivan laser technology, which is quite new and has a lot of huge parameters. We have to know the parameters, we have to know the interactions, which is quite important. And I think this is a good trend, but we have to understand the physics behind. Otherwise, we will not handle this. I think this is a very good trend. We have the lasers, we have the power, we have the wavelengths, we have the fastness of the scanners. I think this trend we have to take and to bring it on the street.
Very good. I don't know if there is any other question. We can perhaps finish, Andreas, with you saw the epic question that is, what can I do for the others? What can the others do for me? So from the perspective of Robert Bosch, what do you expect from the photonics community? What kind of interaction do you expect in these technologies?
I think it would be very good if we act like a family. Sometimes we are competitors, but if we do act like a family, if we improve from each other, for example, with physics, let me start with the basic physics. If one shows, I have seen this from production chain, from this oil has an influence on this has an influence on this, then we can learn from each other and becoming better and better and better. We can increase everything. Then we can use this camera systems. Then we can use this. This is very good for this. So if we spend our knowledge to everyone, for sure we have to keep some knowledge, but if we try to tell a lot of them, which we are allowed to, then we will getting better. Now hopefully I can contribute on this, and hopefully we can act like a big family to improve the stuff for mobility, for example.
Very good. So thank you very much, Andreas, for your time today and the presentation. Thank you.
Thank you.
So we can move to next speaker. So it's a pleasure for me to introduce Pasquale Franciosa. He's the head of Laser Beam Welding Applications Lab at the WMG, the University of Warwick. And he's going to talk about the advancing laser welding using beam shaping, bolster green transport future. So Pasquale, the floor is yours.
Can you hear me?
I can hear you, yes.
Okay,
I don't see your
because
camera, but perhaps you can
for
share.
some reasons, Windows made an update just like a few minutes before this meeting, and then since then the camera again doesn't really work today. So I have to really apologize. I've raised them with my IT people, but they couldn't fix in very very short time. So
I hope you can share anyway.
Yeah, hopefully you can see the slide. Let me just share it now. So yeah, can you see it?
Is it still working on? Yeah.
Yeah. Okay.
You can perhaps move to the full screen, and that's all.
Yeah. Let me see. Okay. Can you see now?
Not yet, but probably in a minute. Yeah. Thank you, Pasquale.
Okay. Yeah. Thanks again for the introduction. So my presentation today is pretty much around beam shaping. Static, but I mean most of the content is around the dynamic beam shaping for e-mobility applications. Okay, so that will be the main topic for today. So just a bit of introduction about I mean where we are and what we do. So we are in the WMG. WMG is the Warwick Manufacturing Group within the Warwick University. So I hope you can see the map here on the right-hand side. So we are physically within the Coventry area. So Coventry is it's literally the middle of England. So we are within the Automotive UK hub. So we have major car manufacturer co-located not far away. And I mean, one of the largest one, probably the largest one in UK, in England, is the Jaguar Land Rover. So we are not far away. So we are very automotive focus. The main focus for us is low carbon mobility. So anything around low carbon mobility. So starting from battery systems, autonomous driving, advanced manufacturing technologies. So everything is really moving around that in terms of research, development, and applications. So the laser welding lab, we have 15 people on board between researchers and student and PhD students. So the team is also, has been growing over the last couple of years, and is still growing. So which is a positive news. So what we do, yeah, you can see here. So we cover those 5 main areas. So going from the fundamental, so the physics of the laser to the material. So laser to material interaction, then the process modeling and digital twin in general, then sensors, monitoring and control. We work a lot in full-scale prototype with end users. So end users are very often coming to us and then asking to develop, obviously, together with their input, the pre-production series prototypes that they can test and then take a decision after that. And this also includes, quite intense testing and characterization. So we can cover pretty much all those 5 areas in a house. And then talking about the TRL level, yeah, this is what I usually show. So we can start from feasibility studies. So eventually understanding, the metallurgy of the material for a given laser input. And then we can go again together with end users all the way up to the TRL 7, which is like full-scale prototyping together with the testing. So yeah, from fundamental research all the way to full-scale prototype. Probably I'll go very quick on this. So the laser lab, we are very laser welding focused. So the lab has been growing, and you can see here, some of the equipment we have available now. I don't want to mention, anything in detail, but you can see some of the, the laser optics, sensors, and software we also have available for process development. So we have recently installed the C1 laser 14 kilowatts, which, and I will show some results now in the next couple of slides. So now let's come to the main point. So production at scale for e-mobility. So now from our experience of working in a battery system related welding projects, yeah, pretty much all the end users are asking for those 5 points. So first is about welding. So novel welding strategies, and these days also becomes quite important the de-welding. So de-welding, it means end of life, or even a repair of the defective module, like a bus bar. And then they are really asking for sustainable strategies, yeah, for enabling welding plus de-welding. So that is an important element. There is a huge demand for new material combinations, especially for mixed materials, steel, copper, aluminum, which probably everybody is aware of. Cost reduction is always a big kill when it comes to laser technology, because obviously compared to other technology, laser is always more expensive. So there is always a, let's say, desire to justify the investment. And one way of justifying the investment is through the core benefit of the laser technologies. Yeah, and the need for zero defects, we know that's very, we are in a, let's say, ideal lab scenario. Yeah, probably we see no defects, but when it comes to real production, there are variations and uncertainty from many places, including surface contaminations. Yeah, and all those, let's say, factors altogether are adding defects, and then controlling defects is is the whole game these days by combining sensors, AI, and digital solutions. And also this is something we see more recently. Yeah, people are asking for training, so upskilling, because they are eventually used with more traditional joining processes, not too much with the laser-based manufacturing, and there is a quite high demand now for upskilling the workforce. Now, the reason why, and this again is from our experience, people are a bit of sometime afraid of using lasers. First is because of the high capex, and this is probably because people are very associating the laser technology to productivity. Yeah. So when we talk about laser, it's about speed. Yeah. So laser is like a fast process by definition. So very often, yeah, we position ourselves on this level. We say, okay, we can use a laser process to maximize productivity, but then we forget about the second benefit of laser, which is the flexibility. Yeah. So laser is a very extremely flexible tool if used in the correct way. And this is where now we see the biggest benefit or the biggest opportunity of the beam shaping, because beam shaping either in time or in space or time and space together. So we see the biggest opportunity. So obviously beam shaping is nothing new. So technologies for beam shaping has been around for probably more than 15 years by now. But only these days, yeah, because of the latest advancement in scanners and also laser systems, and because of the demand from e-mobility, we see people asking more and more for not only productivity, but also for flexibility. So flexibility for us is the next upcoming requirement from the end users. And this is true especially when we are dealing with low volume and high diversification manufacturing. So it means it's not only one product type, but multiple product types. And this is exactly where the flexibility plays a role. So this is where beam shaping, yeah, again, comes into the picture, and is the motivation for the beam shaping. So why beam shaping in the first place? Probably for three reasons. First, because we can have a more optimized weld profile, or we can control the weld profile. Second, and this is probably where most of the people are focusing their effort these days, is the control of the molten pool and the keyhole dynamics, eventually for reducing porosity and spatters. And then another area which we see of interest is the control of the microstructure. Now, statistically speaking, there is a lot of let's say academic work and industrial implementation between the first two areas, so weld profile and molten pool dynamics. There is very little on using beam shaping for controlling the microstructure. Now, there are some academic contributions. Probably there are some few industrial implementations, but most of the emphasis is around the first two. So now we see and we believe that using the correct beam shaping, we can also influence the microstructure, and that's why we have been investing time and effort in doing that. So now the material, which is very a high demand these days, is aluminum. So 6,000 aluminum for especially for producing the battery cases, so battery trays. Yeah, there are many, design, many architecture where end users, OEMs are using those extrusions, especially extrusions for producing battery casing. So the practical challenge is the weldability of the 6,000. So there is an evergreen challenge, which is the sensitivity to hot cracking. So 6,000 are really not very friendly to be welded with the laser. They become more friendly if we put the filler wire. So then it becomes a hybrid process, laser plus filler wire. But if you do that, you are increasing the complexity. Eventually, you have to reduce the speed. You need more power. You need gas. You need wire. So there is more complexity and more cost overall. So welding with the wire is the the state-of-the-art process today, but the industry is eventually aiming, or it's like a wish list, is to go away from wire and then weld fully autogenous. So now this video is clearly showing, a very, nasty crack here opening in the middle of the weld. Is a central line crack. The color map is showing the strain induced by the thermal load, and obviously because of the combination of the thermal load, the chemical composition of the alloy and the microstructure, then you get cracks in the end. So it means those welds are not really functional. So how we want to approach it, is using beam shaping, dynamic beam shaping in particular. So we have been testing over the last few months the technology from C1, so the coherent beam combiner with optical phase array. So now, without going into the technical details of the setup, in essence, is a 14 kilowatts total. Although for the materials we have been using, we have used far below around 3 kilowatts. So it's a combination of 0.4 to 0.8, 60, 61 aluminum in overlap. The requirement is a full penetration weld and obviously structural, so no major cracks. So we test a different shape. So this is one set, starting from a standard single core to something more like triangular or arrow-based shape. And then we also tested something more dynamic. And you can see some of the frequencies we have been using. And those are some of the results now. So those are the tensile load in megapascal for those shapes. So now, if you compare the baseline on the left-hand side, so close to 80 megapascal, and then you see how much improvement you can get by changing the shape. It's almost 20% improvement only by changing the beam profile. And this is like semi-static because it's only one shape. Then if you add the dynamic element, dynamic element with the, given in this case, we didn't go more than 1000 hertz. You can see again the trend. There is a margin for improvement. So this only suggests one thing in the end, that changing the shape from a, let's say, round axial symmetric Gaussian or close to be Gaussian profile to something else, like a triangular profile, has two main benefits. So first, the possibility of changing the thermal gradient, especially in the lateral direction. And then reducing thermal gradient, eventually you are reducing thermal stresses, and reducing thermal stresses eventually because of the impact on the during solidification on the grain structure, there is better chance that the welds will sustain, let's say, the thermal load and wouldn't crack in the end. And the results are quite evident here. So clear benefits we see in using the beam shaping, but there are also clear challenges. And one of the biggest challenges is to say, okay, great, we have all this flexibility, but flexibility comes with a cost. So first, how do we choose the optimal shape? It can be anything, right? So we can start from a core and ring. We can add a triangle on it. We can add a tail beam behind. So that is a big open question. And to answer this question, we have to understand all the physics behind the relationship or the interaction between the laser and the material, the laser and the molten pool with all the multi-physics and the multi-scale element involved. So the controllability challenge is definitely there, which we must address. So the next challenge is acceptance. So more flexibility means more costs for the end user. And we need a clear business case to justify why more flexible means eventually benefit for the end user. The next is the reconfigurability. That means it's not only the laser process alone, but it's the laser together with the jigging, the clamping, and the old automation around. And then talking about the AI and this industry 4.0 kind of logic is the connectivity. So again, it's not like a standalone laser machine, but the machine must be eventually connected, and then we have data collected from the process, and then eventually using AI technology we can have like a smart system in the end. So we took those 4 challenges on board, and the idea was, right, so what about, rather than thinking about an isolated welding process, we have a laser as a service. A laser as a service understood that the manufacturer will be able to produce parts on demand, and then with a rapid repurposing of existing welding equipment, laser welding equipment. So that was the whole idea we had, or the whole motivation behind one European project which we have been granted, that is laser for mass. So the whole idea is a laser as a service for enabling digital platform with dynamic beam shaping for supporting, you know, the next generation factory, which is supposed to be smart, decentralized, and sustainable. Now, answering the question, what can you do for us? Yeah, so the project will be having, we are going to have the kickoff of this project in January, so in a few months from now, and we're really looking for partners or, you know, industrial or even academic members of the industrial advisory board. We already have few members in the advisory board, but we're looking for more members, especially for those companies or for those institutions that they see the benefits or the opportunity of using the beam shaping for controlling thermal cycling and improving eventual material properties, especially within the logic of you know, laser as a service. Okay, so the logic of rapid repurposing and servitization in general. So with that, I close my presentation. So now, if there are any questions, I'm more than happy to take any questions from the audience. Yeah, thank you.
Thank you very much, Pasquale. So as Pasquale mentioned, we have time for questions. You can raise your hand and make your question directly to Pasquale. I could perhaps start with one related to the shape itself in the dynamic beam shaping. I'm thinking in this compromise with end user. So I understand reading between lines that sometimes you need to be in a middle, let's say, solution to have a result that is good enough, but without compromising the cost and the difficulty of implementing the process, right? Mm-hmm. Or does it make sense in the dynamic beam shaping to go to the most complicated shape possible because it's easy to implement and easy also to train the end user?
Yeah, well, I would say no. The short answer is no. So using the most complicated eventually never work in practice. So in practice, probably the optimal solution is always in the middle ground. Yeah, because welding, especially laser welding, is always a compromise between multiple requirements. So starting from the power usage, the thermal distortion, weld quality, and weld quality is a combination of many parameters like cracking, porosity, concavity, convexity, penetration depth. So it's a mix of many requirements. So I think the compromise between complexity and cost is about developing some intelligence on it, right? So eventually the end user will invest in this let's say flexible technology if there is a graphical interface or software, yeah, which will be guiding through the selection of the shape, for example. So like, you know, using multi-physical CFD simulation is one element, yeah, because eventually you can predict the behavior of the laser to material interaction through the simulation. But if you do that, the simulation is also quite time consuming. Yeah, it doesn't take like few seconds, it takes few hours. And then another question coming, okay, right, simulation is the right approach, but how do we make the simulation more, let's say, not real time, it's impossible, but close to real time. Yeah, so there are elements to consider. And then quality, right? Then how do you assess the quality in process? And then, yeah, again, the same logic, we have to deploy sensors. We have Marcus Prezitek, which is, you know, the lead company in this area. So those are other elements to consider. And then all the AI, yeah, the AI element for, you know, learning from past data, past experience. So I think all those key technologies must be combined in a consolidated way. In such a way, we have a flexible tool. We have intelligent, you know, digital technologies, and then in the end, we can offer to the end user a let's say platform which is really justifying the investment.
Mm-hmm. Very good, very good. So yeah, I think there is no more questions. So thank you again. Thank you for introducing Pasquale, the new project, and yeah, for let us know that you are also open to discuss with companies to be like part of this advisory board. So yeah, we will talk also about this later on.
Mm-hmm. Yeah, thanks. And EPIC is part of the project anyway. I didn't mention before, but EPIC is a great partner in this project. I mean,
correct.
We have a collaboration as well on this.
We will present the laser formats in the future events, and yeah, open to discuss with any interested company in how to collaborate. So Thank you, Pasquale, for being
Thank
this
you.
afternoon here.
Thanks,
Thank
Antonio.
you very much. And we go with our last speaker. It's Alex Griffiths, lead engineer at Power Photonics. Alex, sorry that you are a little bit late, but we are very happy to have you here and to talk about the freeform beam shaping solutions for laser welding. A lot of beam shaping today, so it's clear, as Andreas mentioned, that it's a trend. So, Alex, the floor is yours.
Yeah, thank you. And can you see my slides?
Yeah, now it's going to full mode. Yeah, everything good.
Great, thank you. Yeah, so thank you for the introduction. I'm a lead engineer in product development at Power Photonic. We're a optics manufacturing company based in Scotland, just outside of Edinburgh. We make freeform optical components, and today I'm going to talk a little bit about our beam shaping optics for optimization in laser welding. So I don't think I need to convince this audience that why we're using laser welding for manufacturing electric vehicles. But even with the advantages of laser welding, there are a number of challenges presented by welding electric vehicle components. Things like the weld geometry and welding of dissimilar materials mean you really need to optimize your process. There's a number of parameters you can play with to get the best performance out of your weld, either from the laser side or from the side of how you deliver that energy to the workpiece. With beam shaping, you're really pushing that beam delivery to its logical limits and putting the power exactly where you want it to be. So on the right here, I've got some example outputs from beam shaping options that we've manufactured at Power Photonic. So we've got sort of standard homogenizers where we can get a uniform flat top, either circular, square, or whatever geometry required. The increasingly common rings or core and ring geometries. We can also do rectangular shapes, or in the bottom right here we have some of that are more unique to us. We have asymmetrical beam shapes. So as we've heard today already, there's a number of ways you can do beam shaping. There's optical methods, in-fiber methods, coherent beam combination. Well, Power Photonic, the way we do beam shaping is with refractive optics. So there's an example here on the left. These are thin plates with a shallow machine surface on them. They're very low footprint into your optical system. So on the right here, I've got a basic outline of your optical setup. If you have a laser source, collimating lens, and focusing lens, this is an additional plate that you slot into your optical train and somewhere in between your source and your focus, and it'll generate the shaped profile at focus. The incident light's refracted. The surface is finely controlled to impart a specific divergence to your laser beam, and that adjusts the shape of the profile that you get as the output. A little bit on our manufacturing process. So we have a laser-based manufacturing process that's been optimized for fused silica. Starting with a flat substrate, ablation produces the large-scale structure of your optic in a point-by-point manner. And then afterwards, the surface is laser polished. This reflows the surface and produces an optically smooth finish. This means we retain the bulk properties of fused silica. We have high power handling and low surface roughness, which means low scatter. This point-by-point addressing of the surface means that we have truly freeform optics. It lifts a lot of the conventional restrictions on optical manufacture, where you might need rotational symmetry or mirror symmetry. We don't have any of that, so that gives us a huge amount of flexibility in terms of what outputs we can generate. So there's some examples here of we can make flat tops, we can make beam splitting outputs with multiple spots, the core and ring, and then this tail shape output, which is an asymmetric one I'll come on to in a minute. In terms of how you install these into a practical system, for R&D trials, we've had some good results so far by replacing a protective window with one of our optics. So these process heads will typically have at least one protective window somewhere in the system. We can remove that, replace it directly with an optic of the same geometry to generate the beam shape at the output. This is good for a quick test. Might not be practical for a full manufacturing system. These really aren't sacrificial components, and you don't want to treat them as such. But for a more permanent installation, we've got an example here on the upper right, where we have a tray that sits into a low-profile module, where you can add the beam shaper or remove it as needed, or swap the beam shaper to generate different outputs. This module could sit anywhere within the process head. We typically prefer it to be in the collimated path, but it's just as another design consideration to mount it somewhere in the diverging or converging positions. And similarly for a scanning head, if you've got a Galvo scanner, we would mount this somewhere before your scanner, ideally in the collimated path. So moving on to some actual beam shapes, the core and ring shape is becoming quite commonplace. There's a number of ways to generate this and a number of solutions out there already. Something quite specific to our method of generating this is we get a long depth of focus. So you get a core and ring caustic, not just a core and ring profile. This here is our simulated results with focal position in the middle. Before focus and after focus, that core and ring is maintained. And then we have a measured version here as well. So we get good agreement between simulation and measurement. We've done some application trials with this for welding of aluminium 6082 in an autogenous manner, so no filler wire and no shield gas. And this high-speed video here is the welding, well, not real time, in slow motion. So we see improved melt pool stability during the welding. There's a reduction in the amount of spatter coming from this core and ring beam. And the headline result from this is that we got nearly a 50% increase in the tensile strength of the material after the weld was done compared to welding with no beam shaper. Moving to something more unique to us, we have this tail, what we've been terming the tail shaper output. So this is an asymmetric beam that's been tailored to match the asymmetric nature of the welding process. So we have this linear shaped spot that would translate in the direction of the weld. You have this high intensity spot here that's still generating the keyhole and performing the weld, and a lower intensity tail that follows it behind. Again, we've got good agreement between what we simulate of the intensity profile through the beam shaper versus what's measured in reality. And here we've got some screenshots from the high-speed video of where we have no beam shaping, you get this round keyhole. And with the tail shaper, you get an elongated keyhole and a trailing tail behind it. These particular trials were done in an aluminium alloy. And we also have some similar results from simulation that indicate that this elongated keyhole from the asymmetric profile reduces the probability of seeing porosity within the weld. So there's some examples on the right here, the unshaped beam, you get these large pores left over from air bubbles trapped in the weld. And we don't see the same effects with the tail shaper. This set of results is our last set I have today. This is a customized beam splitting optic that we developed, where we've aimed to have a 3-spot output with the two of the spots trailing the main spot with 50% intensity, 50% of the intensity, and these would be separated laterally either side of the weld. This shows a strong influence on the weld's geometry, on the geometry of the weld seam. So here on the left, this is the case with no beam shaping, whereas when we have these additional spots, the width of the seam at the top is much wider. But also you can see there's a variation in the profile, so it peaks here in the middle. And if you reverse the direction of the beam shaper so that the 2 spots lead the main spot, this shape changes as well. So directionality is important, and we can have a strong influence on the cross section. So to conclude, I think I've demonstrated that these refractive freeform beam shapers provide flexible intensity patterns with simple system modifications. It's a straightforward addition of a single extra optical component. And the intensity patterns can be tailored to affect key parameters in the welding. What we can do for you is provide beam shaping optics and highly customized freeform intensity patterns to enhance various processes. And what we're looking for from others is to see the challenge, to be presented with the challenges seen in laser applications, so that we can collaborate on optimizing these intensity profiles for a specific application. Just to finish, I need to acknowledge that as an optics manufacturer, we don't have capability to do welding in-house. So these trials have been done with some of them with Fraunhofer IWS and some of them with WMG, with Pasquale's group, who we've just heard from. So thank you for your attention. I'm happy to take any questions.
Thank you very much, Alex. So we have time for questions. So I can perhaps start with a question. Is about welding in dissimilar materials. Do you have any tests in this application? Because you presented some aluminum. That is also interesting. But do you have any tests with dissimilar materials?
Not yet. It's certainly something we'd be interested in trying, particularly in copper as well. But so far, all of our trials have been in aluminium 6082, the aluminium alloy in this one, and stainless steel.
Very good. And regarding this, the multi-spot outputs is something that you have in mind to explore more in detail to create more spots. Is something that you see potential for other applications, or is quite specific for this particular type of welding?
I think that the current embodiment of it would have to have a very specific application for this weld seam shape to be useful. Really, this is the first data point to say that this kind of beam shape can give you variability in that seam. So if that's something that's useful to a particular weld, it's something we can explore further. I am interested in less about the multiple spots and more filling in that gap. Because of this welding being a thermal process, I don't think that extinction between the spots is that critical. So this sort of triangular output may be more optimal, and maybe bringing that power inwards a bit, less of a wide profile, would be beneficial.
Very good. Very, very interesting. I don't know if there is any final question for Alex. I don't see anyone in the chat. And if not, thank you again, Alex, for nice presentation and great results in combination with Fraunhofer IWS. So thank you for being here this afternoon. And thank you, everybody, for attending. I hope you found all the presentations interesting. It was quite nice, a set of different approaches. We saw the static beam, the beam shaping, dynamic beam shaping, also the contribution of CO2 lasers, challenges by Robert Bosch, the combination of beam shaping and AI from Precitech. So I think we discussed about a lot of different topics, and then of course the process monitoring presented by NIT, for example. So thank you to all the speakers for being here today, and thank you to all the attendees. As I mentioned, we are going to have more discussion about laser processes, in particular for automotive and e-mobility, but also in other applications. So I hope to see you again in future EPIC meetings. So thank you again, and good afternoon to everybody.
Thank you very much. Bye.
Thank you very much, Antonio.
Thank you, Dave. Bye bye. Have a good afternoon.
Bye.
Thank you, Germán.